So in this video we are going to discuss singular matrices, which are matrices where the determinant is equal to 0. And the aim for this video is going to be to understand how these three statements are equivalent to one another. So the first statement is that the determinant of our matrix A is equal to 0. And A here is a general square matrix, so I'm not specifying what n is. It's an n by n matrix. What we're saying here is going to hold no matter which n you pick, no matter how big your matrix is. So if the determinant is equal to 0, I claim that this is equivalent to the statement that the rows of the matrix are linearly dependent row vectors. So if you look at the rows in your matrix, and I might just actually draw out our matrix. So here we have our matrix A11 all the way up to A1n, AN1, and then in this corner it will be ANN. So in total, we have n rows. Here's row 1, here's row 2, here's row 3, all the way up to row n. And each one of these, if you view them as a row vector, is a row vector in Rn. So it's a n component row vector. So you look at these n row vectors that you've got making up this matrix, and I claim if the determinant of the matrix is 0, then the rows are going to be linearly dependent vectors, meaning that there is a non-trivial linear combination of them that gives the 0 vector, or equivalently that one of them can be written as a linear combination of the others. So I claim the determinant of the matrix is 0 if and only if the rows are linearly dependent row vectors. So these two are utterly equivalent to one another. The second equivalence, the third statement, is that the determinant of the matrix being 0 is also equivalent to saying that the columns of the matrix, viewed as column vectors, are going to be linearly dependent. So again, you've got n columns in this n by n square matrix. Each of them is a column vector inside Rn. Each of them has n components. And I claim that if the determinant of the matrix is 0, this is true if and only if the columns are linearly dependent. So I claim these two equivalences are there, and therefore if those two exist, I can put in a third equivalence here between the rows being linearly dependent and the columns being linearly dependent. So if this one's equivalent to this and this one's equivalent to this, then obviously it follows that this one is equivalent to this one. We will focus on proving these two equivalences, and therefore we will get this one for free. Now I do have a brief point that I'd like to make here, and I do intend to keep this brief because if I'm not careful I could get completely sidetracked onto this, and this is not the purpose of this video. But many of you will probably be aware that matrices can be associated with linear maps between vector spaces. And we have got our maths hat on at the moment, not our pure maths hat. So we are thinking just in terms of real matrices, and they're going to be representing linear maps between real vector spaces. If we're dealing with an n by n square matrix, those maps will be maps from Rn onto Rn. And many of you will also know that there are two major linear maps that can be associated with a given matrix. You can either think about it sending all vectors x onto A times x, where the vector here needs to be viewed as a column vector, and then you're multiplying with the matrix from the left, so the matrix is on the left and it's multiplying onto the vector that's in the right position. Or you could instead think about your vector as being a row vector, and then you could multiply it with your matrix on the right. So you could take your row vector, multiply it with the matrix in the right position. This would give another row vector. These are the two major linear maps that can be associated with a given matrix A. Now, if the columns are linearly dependent, that's going to mean that this linear map here is going to be mapping Rn onto a smaller subspace of Rn. It's going to be a non-bijective, non-surjective, non-injective map. If the rows are linearly dependent, it corresponds to this mapping being similar. It means that as a mapping, if you look at the range, the portion of Rn that is actually mapped onto, it's not going to be the entirety of Rn, it's going to be a subspace of it. Therefore, if these things are true, then the linear maps that are associated with the matrix are non-invertible linear maps, and therefore the matrix cannot be invertible, otherwise it would mean that the linear map was going to be invertible. So I'm not going to say much more about that. The reason I've raised that is just to highlight the points that the determinant of a matrix equaling 0 therefore corresponds to it being a non-invertible matrix, corresponds to it representing these linear maps that are non-invertible because they are not bijective. And the reason for that is because it corresponds to the columns being linearly dependent and the rows being linearly dependent. So I'm not going to say anything more about that because the focus of this video is now just to prove this. That was really a future directions thing where we will take this. So let's turn our attention now to proving these equivalences here. And a warning, the proof of these is not completely simple and it's going to be quite fragmented, so we're actually going to have to prove a whole bunch of other theorems that you will probably think, what on earth does this have to do with what we're trying to prove? But you will see how these other theorems that we're going to prove will build up and allow us to eventually get where we want to go. But it is going to feel a little bit unmotivated at times, and you probably will be screaming at your computer screen, what on earth does this have to do with what I'm trying to actually prove? But I ask you please to bear with the groundwork. And hopefully looking at what we're trying to prove, you should see that this is not going to be a trivial proof. I mean, this determinant, we've defined this in previous videos in this playlist on vectors and matrices. You know, it's this sum of all these products where the products are of n things and the things are entries from the matrix. And you've got to select the things that you're producting together such that you end up with one representative from each row and each column and only one representative. And we've seen how there are different products that achieve that. And then you don't just add all these possible products together. Instead, some of them have pluses in front of them, some of them have minuses in front of them. And whether they have a plus or a minus in front of them depends on, you know, how badly they are off the diagonal. You know, if you colour in which ones you've selected on the picture, how off diagonal the entries are, and it's to do with how many switches would you have to do to get the entries back into the diagonal position. And if it's an even number of switches, then it's an even permutation product, and it would have a +1 in front of it. And if it's an odd number of switches that you'd have to make, then it's an odd permutation product, and therefore it has a minus in front of it. So a very complicated thing, the determinant. So the determinant equaling 0, what on earth does this complicated thing that we've defined, equaling 0, have to do with the rows and columns being linearly dependent to one another? It's not immediately obvious why this is true whatsoever. So it hopefully should be apparent to you that this isn't going to be a completely trivial proof and is going to require some groundwork. So bear with the groundwork. It's not avoidable, I'm afraid. So the first thing then that I'm going to prove to you is that if you have a row in your n by n matrix, and again I'll remind you everything we do in this video is going to be for a general n by n matrix. Sometimes I might use examples of 3 by 3 matrices, but everything's going to hold true for the general n by n case. So if you have a row that consists entirely of zeros, or indeed if you have a column that consists entirely of zeros, the determinant of that matrix will equal 0, i.e. it will be one of these singular matrices. The proof of that is very simple. Laplace expansion we know is a valid way to find the determinant of a matrix. So we can do Laplace expansion using this row. So we'll then have all the coefficients in the Laplace expansion will be zeros. If we were to do Laplace expansion for this, it would be, we'll take this first one 0 times the determinant of its reduced matrix. It doesn't matter what that matrix is because it's 0 times whatever that determinant is, so it will go to 0. Then the next one will be plus or minus, we don't care which, 0 times the determinant of its reduced matrix. So this bit, this bit, this bit, this bit. Again, it doesn't matter what the determinant of that is because it's all being multiplied by 0. And you get the idea. You go on, all of them are going to be multiplied by 0. Therefore, the determinant is overall going to come out as 0. And similarly, if you have a column of all zeros, again, you can do Laplace expansion using that column. And again, all the coefficients in front of all the determinants, it doesn't matter whether they've got a plus or a minus, they're all going to be 0, so it's going to come out overall as 0. So that's the first thing then, that if you have a column or a row of all 0 entries, then the determinant of that matrix will equal 0. So our next groundwork theorem is what happens to the determinant if you take a row or a column and multiply all the entries in that row or column by some constant. So we'll have our example here. Again, we'll deal with an n by n matrix, and just for the sake of this picture, we'll look at this first row, so A11 all the way up to A1n, but this applies for any row, and it would also apply for any column. And the determinant of this could be any real number, indeed it could be 0, this is still going to apply if the determinant is 0. We'll just call it det A. Now let's think about a new matrix where we have left all the rest of the matrix completely the same, but we have multiplied everything in this row by a constant, which we'll call lambda. So this entry is now lambda A11, this entry is now lambda A12, etc., lambda A13, all the way up to lambda A1n. And as I say, every other entry in the matrix is the same. The claim is that the determinant of this matrix is now the determinant of the original one times lambda, so it's lambda times det A. How can you see that? Well, again, just use the Laplace expansion. If we were to do the Laplace expansion using this row, then we'd get that this is lambda A11 times the determinant of its reduced matrix. So writing a little bit of this out, lambda A11 times the determinant of that reduced matrix. But that reduced matrix here is exactly the same as the reduced matrix over here. If we did Laplace expansion with that first row over here, we'd have A11 times the determinant of that same reduced matrix. So this thing here is the same as what you've got here. Carrying on, the next one we're going to have minus lambda A12 times the determinant of its reduced matrix, which is going to be this bit and this bit here. And it will again have a corresponding term over here. So the corresponding term over here would be minus A12 times the determinant of that same reduced matrix, because the reduced matrix bit hasn't changed. So again, colouring this in, this is exactly the same as here. And you can see it continues on. Lambda A13, you'll have plus lambda A13 times the determinant of its reduced matrix, but the reduced matrix determinant will be exactly the same as the one over here. So you can see that overall you will get the exact same thing as you would have got here, but it's all just multiplied by lambda, hence how the determinant is going to end up as lambda det A. That same argument is going to hold true no matter which row it was. So if it had been a row down here that you'd multiply through by a constant, it would still hold true by this Laplace expansion argument that the determinant will come out as just lambda times the original determinant. And the same would hold true if we took a column. You know, if I write this out, so if we had a column here, let's say we'll have column 4, A14, A24, all the way down to AN4, and you multiplied it through by lambda here, so all these entries have been multiplied by lambda, then if we do Laplace expansion around here, we'll just get all of these as the coefficients in front of determinants, but all the rest of the matrix hasn't changed, so their reduced matrices that you're taking determinants of will all still be the same, and therefore in this great big sum that you get, it will just be lambda times the sum that you would have got from taking the determinant using Laplace expansion of this column when you didn't have the lambdas there, i.e. for the original matrix. So that's theorem number 2. Theorem number 3 now is really interesting. Those two were a bit boring, easy to prove. This one's really beautiful. A bit of induction now. So theorem number 3 is what happens to the determinant of the matrix if we swap two rows or we swap two columns. And again, for the picture, initially, we'll just take rows. So what we can imagine doing is having two rows, and we'll take, for example, the first row. So we'll have A11, A12, all the way up to A1n. And then the other example we'll take is A31, so row 3, A32, all the way up to A3n. And then, of course, the matrix continues on down to the nth row, AN1, all the way up to ANN. So what we are now wondering is what happens if I take all the entries in this row and I bring them up and put them in the first row, and take all the entries from the first row and bring them down here. So I create a new matrix where they're swapped around, and I will draw this out. So the new matrix is going to be A31, A32, all the way along to A3n. Row 2 has remained the same, that hasn't changed, but then row 3 has changed. It's now got the entries of row 1 there, so A11, A12, all the way along to A1n, and then the rest of the rows in this matrix haven't changed. The nth row, for instance, is still exactly where it was, so AN1, ANN. So this is our new matrix, and the question is, what is the determinant of this new matrix? And my claim is that if this is determinant A, so if this has determinant det A, then this one has determinant negative det A. So switching two rows, or indeed switching two columns, the proof is going to work the same way, changes the sign of the determinant from positive to negative. So how am I going to prove this? I'm going to prove this by induction. So we're going to start with the base case. And the base case is not going to be a 1-by-1 matrix, because in a 1-by-1 matrix you don't have two rows to swap. So we have to start with a 2-by-2 matrix. So A11, A12, A21, A22. So hopefully everyone knows what the determinant of this matrix is. It's A11 times A22 minus A21 times A12. Now if we swap those two rows, so now A21, A22, A11, A12 is our new matrix. The determinant of this new matrix is going to be A21, A12, so these two multiplied together, minus the off-diagonal terms multiplied together, so minus A11 times A22. And you will note that that product there, or rather that sum there, sum of products, is minus what we have here. If you multiply this by minus, you get that. So it holds true in the 2-by-2 case, works perfectly. So that's our base case checked. Now what we want to do is assume that it holds true for an n-by-n matrix. So we assume it's true for n by n, and then we want to prove that it will hold true for the n plus 1 times n plus 1 case. And if we can prove this inductive step, then because it's true for 2-by-2 matrices, this will then imply that it's true for 3-by-3 matrices, and then because it's true for 3-by-3, it will then imply it's true for 4-by-4, etc. 4-by-4 will imply 5-by-5, i.e. it will be true for all n-by-n matrices, apart from 1-by-1 where it's too trivial. You know, you can't swap rows in a 1-by-1. So, how are we going to prove our inductive step then? So, we've assumed that it's true for n by n. Now let's consider an n by 1, an n plus 1 times n plus 1 matrix. So we'll draw this out here, and we'll again consider moving two rows around. And just for simplicity, we'll take the first row and the third row. So A11, just for the picture though, that is, it won't be crucial at all in the proof. It's just so that I've got a picture to point at. A31, A32, A3n. There's the third row. So we're going to switch those two rows, and then it goes all the way down now to AN plus 1, 1. AN plus 1, 2. Looks very confusing, these indices. Hopefully you'll cope. N plus 1, N plus 1 there. Oh, and I've already made a mistake. This should go to N plus 1, this bit here. There we go. So here's our N plus 1 by N plus 1 matrix. And we're now going to imagine switching two of the rows. Oh, and actually, before... no, we'll continue on. I was going to go back up to this. In fact, I am going to go back up to this 2-by-2 case. Because actually, this holds true not just for rows, but also if you switch the columns. So I will actually just prove the base case now, and then we'll prove the inductive step. So if you again consider this 2 by 2 case, so A11, A12, A21, A22, again its determinant is nicely written here. Now consider swapping the two rows rather than the column, now consider swapping the two columns rather than the rows. So turn it into A12, A22, A11, A21. So we have switched the rows this time, whereas here we switched the columns to get that. Here we're switching the, and I keep saying the wrong thing, I'm sorry, it's been a long day. So here we have switched the rows to get this. Here we are switching the columns to get this. And I want to prove that the theorem still holds true even if we switch columns instead of rows. So again, I'm just doing the base case first and then we'll go on to the inductive step. So we've switched the two columns, we've got this. What's the determinant of this new 2 by 2 matrix? It's going to be A12, A21, so the diagonal terms multiplied together, minus A22, A11, and you can see again, that's exactly the same as this thing, i.e. it's the negative of this thing. So for 2 by 2 matrices, if you switch the rows, it turns the determinant to the negative. If you switch the columns, it also turns the determinant to the negative. So the theorem is true for both rows and columns in the 2 by 2 case. Now what we're going to do is the inductive step, and initially we're doing it as for this picture with just rows. We're imagining we're going to switch these two rows, but I'll show you how the proof is going to hold true for columns as well, and therefore we will have proven by induction that if you switch any two rows or any two columns in an n by n matrix, it will turn the determinant to the negative version. So how are we going to proceed then? How are we going to prove that if we switch these two rows, so now let's draw out the matrix with the switched two rows. So we've switched row 1 and row 3, so A31, A32, all the way up to A3n plus 1. Row 2 remains unchanged, and then we have row 1 now in row 3's position, A11, A12, all the way up to A1n plus 1, and then we go down to the n plus 1th row, which hasn't changed, an plus 1, 1, an plus 1, 2, all the way along to an plus 1, n plus 1. Good. So I want to prove to you that this thing's determinant is going to be minus the determinant of this. So again, we'll call the determinant of this det A, and we want to prove that this thing's determinant is negative. And what we are allowed to assume is that the theorem was true for n by n matrices, i.e. that if you have an n by n matrix and you're asking what is its determinant and you have switched two rows in that n by n matrix, the determinant will be the negative of the original determinant. So we're going to use Laplace expansion here because Laplace expansion reduces the problem of finding the determinant of this n plus 1 by n plus 1 matrix down to the problem of finding the determinant of n by n matrices, and then we can apply the inductive assumption that the theorem is true for n by n matrices. So which row are we going to choose, or column are we going to choose? And we will have to use a row actually in this case because we've swapped rows. If we'd swapped columns, we'd use a column. Which row are we going to use to do Laplace expansion around? Well, we're going to use one of the rows that isn't involved in the switch. So as long as you're dealing with matrices that are bigger than 2 by 2 matrices, which we've handled as a special case, it was our base case, there will always be another row that isn't being switched because you're only switching two rows. So for 3 by 3 on, you'll always be able to find one row that has remained constant. So we could, for instance, take this row here, the bottom one, and we're going to do Laplace expansion around it. So let's go through this. So we'd start with this one here. We'd have it out the front with a plus or a minus in front of it. So I will put the plus or minus there. An plus 1, 1, because we're not bothered about whether it has the plus or the minus. That's not crucial to our proof. And then it will be the determinant of this reduced matrix here times this determinant. And now I want to also write out what the determinant would have been over here. So over here, if we do Laplace expansion on the original n plus 1 by n plus 1 matrix, again using that same row, we would have had an plus 1, 1 times the determinant of this reduced matrix here. Now, this reduced matrix here is not the same as this reduced matrix here, but the coefficient is the same, and whether it has a plus or a minus at the front is also the same. So that bit remains the same, but this isn't actually the same. Why is it not the same? Because now this row here and this row have switched in this reduced matrix. But I know something about n by n matrices. I know that the theorem is true for them. I know that if I switch a row, which I have done, this row here, ignore these, they're not part of this reduced matrix, but this row here and this row here have switched. That's the only change that I've made. Therefore, I know that this determinant here is going to be minus. So I'll put that in. This one is the minus version of this one. And it continues on this pattern. So if you look at the next one, again, it will have a plus or minus in front of it. We don't know which. It doesn't matter. We don't need to know because it will be the same as whether there's a plus or a minus over here. So you'll have n plus 1, 2 there. And then in this original one, where would its reduced matrix have been? So cross that line, column out, cross this row out. So it would be made of this column and then all of this. And similarly over here, it would be made of this column and then all of this. Those two matrices are going to be exactly the same apart from the fact that, again, two of the rows have switched. So you'd have the determinant of that reduced matrix over here, and now you've got the determinant of a slightly modified matrix, but it's just that the two rows have switched, and therefore this one, again, is going to be minus of what this one is. And it continues on. So in this Laplace expansion, all of the determinants that appear here will have had this row switched, and therefore will all be the negatives of the determinants as they appeared in this original Laplace expansion for the original matrix. And therefore this entire thing is just going to be the negative of this, and therefore you are going to get that this is minus det of A. So from the inductive step, using Laplace expansion with a row that isn't involved in the switch, you can prove that the theorem is going to be true for n plus 1 by n plus 1 matrices. So the inductive step is therefore proved for this row switching, and since it's true for 2 by 2 matrices, it's then true for 3 by 3 matrices, for 4 by 4 matrices, etc. Now let's just think about doing columns instead of rows. So the exact same thing is going to hold true. You just do Laplace expansion around a column that's not involved in the switch. So I'm not going to write it out as fully as I did previously. So let's say we have a column here and a column here, and those are the two that are going to be switched. So we'll call this one actually the red column, and we'll call this one the blue column. So in our new matrix, the blue column is going to be here, and the red column is going to be here. And we're again doing a proof by induction, so we're allowed to assume that the theorem is true for n by n matrices. We've already proven that it's true for 2 by 2 matrices, and we now want to prove that it's true for n plus 1, that should say. We want to prove that it's true for n plus 1 by n plus 1 matrices. So this is now an n plus 1 by n plus 1 matrix. And we are making this switch of two columns, and we want to prove that this thing's determinant over here is going to be minus the determinant of the original one. So again, all you do is you pick a third column. Let's say we could pick the column right on the end here in green, which isn't involved in the switching. And again, because we're dealing with matrices larger than 2 by 2, you'll always be able to find such a column. It doesn't need to be the one on the end. You could have picked any other one that's not involved in the switching. And then when you do Laplace expansion, so you go through each of the entries here, and if you compare the Laplace expansion for this final one, the one after the switching, to the original one, it's going to be very, very similar. So for example, with this first entry here, you're going to have it here with a plus or a minus times the determinant of its reduced matrix, which is this thing here. So take away the first row and take away its column. And then if you look at what it's going to be in the altered matrix, it's going to be exactly the same. You'll have the exact same entry here with the same plus or minus. and you look at its reduced matrix, again, the reduced matrix is going to be exactly the same apart from the fact that now it's had one of its columns switched with another column. And we know that the theorem is true for n by m matrices, which this is. Therefore, that determinant of that switched matrix is just going to be minus of what's in here. And that same argument is going to hold true as you go down all of the different entries here. So you're just going to get a great big Laplace expansion where all of the determinants are just the negatives of what they are over here, and the coefficients in front of the determinants are all the same. And therefore, the overall thing is just going to come out to be minus what this one's is. Hence, its determinant is going to be minus the determinant of the original matrix. So quaerat demonstrandum by proof by induction.